Okay, so if you recall, this is the problem that we did last time. We wanted to actually generate a random sample of size 10 to the power 5 from this distribution. Okay, and we use the fact that we we can actually generate random numbers from uniform distribution and then use the inverse of the CDF, okay, to generate random numbers from this distribution. Okay, so that is exactly what we did. So you are basically draws from uniform distribution, 10 to the power 5 draws from the uniform distribution. As we can see over here in the histogram plot, that this is kind of uniform from 0 to 1. Okay, but when we actually took the inverse of the CDF, which is square root of u, okay, because x squared is the CDF, so square root of u is the inverse of the CDF. So if we take square root of u, so u are uniform draws, and if you just put square root of u over here, okay, and then plot the histogram for x's, we found that we got this triangular distribution, okay, which is exactly given by this CDF. So how is this given by this CDF? Because what is the derivative of the CDF when x is between 0 and 1? It is 2x. Okay, and 2x is a triangle, right? I mean, it's a straight line, from 0 to, so as x goes from 0 to 1, the PDF goes from 0 to 2. Okay, so it is going to be like again a triangular distribution. Okay, so that is how you can actually use uniform distribution to generate random numbers from any distribution of your choice. And that is why it is very, very important. Okay, so this is universality of uniform. Any questions about this? Okay, okay, then so let's continue. Okay, okay, let's look at exponential distribution as well. Okay, so let's go to scipy.stats, continuous statistical distributions. Okay, in continuous statistical distributions, we can look at exponential distribution. So this is exponential distribution. Okay, so you can easily see this is the implementation. Okay, so it's scipy.stats.expon. Okay, so all that you have to do is from scipy.stats import expon. Okay, so let's do that. Okay, and then we can basically answer some questions. Okay, so let's just write some questions that we would like to answer for exponential distribution. Okay, so let's plot maybe couple of PDFs. Okay, so plot the PDF of x okay, and let's say exponential 1. Okay, and let's say exponential 4. Okay, so we want to plot the PDFs of x and y, where x is exponential 1 and y is exponential 4. Okay, and also answer some questions like this. Okay, let's say we want to figure out the 90th percentile for both of them, x and y. Okay, so determine the 90th percentile for random variables x and y. Okay, what else? We can, well, we can figure out the probability that x takes value between 1 and 2. Okay, and we can also do the same thing for y. Okay, let's do this. Okay, so I give you you know 5 minutes. You try and do this, and then I'll do it. Okay. Okay, so basically, this is how you're going to do it. Okay, so it's actually the scale parameter that you'll have to change. So
Scale is given as 1
for
by lambda.
so scale is basically your so if lambda is 4, the scale is basically 1 by lambda. Okay, that's what it is. Okay, uh, so you know so if you want to actually plot the PDFs, okay, you can again, because exponential random variable takes only positive values. Okay, so you can actually again create x as np dot range. Okay, just create from 0 to 10, for example. Okay, or maybe 0 to 20. Okay, and let's say the increment is by 0.01. Okay, and then all that you have to do is just create probs. Okay, let's call this probs 1. Okay, so probs 1 is x expon dot pdf. Okay, and the input is x's. Okay, so for exponential 1 you don't have to do anything. I mean, it's just by default exponential 1. Okay, for probs 4, okay, where lambda is 4, the scale parameter will be 1 by lambda. Okay, so 1 by 4. Okay, so expon dot pdf x scale equal to 1 by 4. Okay, so that's your probs 4. Okay, and now you just use I mean, let's just plot it in the same graph. Okay, so plt dot plot x probs 1. Okay, and then plt dot plot x probs 4. Okay, and plt dot show. Okay, let's run this. Okay, so let's just add a label. Okay, label equal to, okay, and then label equal to, okay, and then plt dot legend. Okay, sorry. Okay, yeah, so this is for exponential 1. Okay, and this is the one for exponential 4. Now obviously, for exponential 4, because the rate at which the success occurs is or rate at which the uh, arrival occurs, or whatever it is, is higher, so it is very likely that you'll not have to wait a lot to see the occurrence of the event. Okay, so that is why you are getting very high probability density for smaller values of x. Okay, so just for more clarity, because this is beyond 5, actually, this is close to 0, so we can actually just restrict ourselves from 0 to 5, to just see this more clearly. Okay, is this fine?
Yes, Professor.
Okay, so these are exponential, these are the density functions for exponential 1 and exponential 4 respectively. Okay, and now we can actually determine the percentiles, in the usual way. You know that this is ppf function will give you the percentile, so let's just quickly do that. So expon dot ppf. Okay, uh, so uh, so let's do that for exponential 1 first. Okay, so for exponential 1, you just need to specify what percentile you're interested in. So I'm interested in the 90th percentile, and so by default it is exponential 1, so I don't have to specify the scale parameter. Okay, and then print expon dot ppf 0.9 scale equal to 1 by 4. Okay, so this is the answer to the second question. Okay, let's run this. So you can see that 90th percentile in case of exponential 1 is 2.3. Okay, so basically 90% of the probability mass is below 2.3. Okay, uh, and for exponential 4, because the success occurs quickly, rate of successes is faster in case of the exponential 4, because 4 is the rate parameter compared to 1, it is bigger. Therefore the 90th percentile is smaller, for exponential 4 random variable compared to exponential 1 random variable. Is that okay? Is that
Yes.
okay? Okay, we can similarly figure out these probabilities. Now this is something which is easy. We can use the CDF to figure out probability that x takes value between 1 and 2, and probably that y takes value between 1 and 2. Okay, so print expon dot cdf. Okay, so between 1 and 2, right? So 2 minus 1. Okay, similarly we can do the same thing for the other one. Okay, it's just that we have to also specify the scale parameter. Okay, so scale is 1 by 4, and here also scale is 1 by 4. Okay, let's run this. Okay, so you can see that there are 23% observations uh, between 1 and 2 when we are talking about exponential 1 random variable, and when it is exponential 4 random variable, then there are around 1.7 1.8%, okay, observations between 1 and 2. Is this fine?
Yes, Professor. That's
Okay, okay. Okay, so let's now discuss some other important concepts. Oh, by the way, as you can also figure out the mean and the variance and all that stuff. So as you can see over here, you can just figure out the mean. Expon dot mean, expon dot var will give you the variance. Expon dot standard deviation std, will give you the standard deviation. Yeah, I mean, so basically you can figure out all these things as well. Okay, okay, so now let's move on to some other important interesting stuff, which is law of large numbers and central limit theorem. We have already seen some applications of law of large numbers in this class, but we'll see some more. Okay, and I'll give you precisely what it means, and how is it useful, and we'll also do some examples like how we can use it to solve problems. Okay, so let's talk about that now. Okay. Okay, so before we do law of large numbers, okay, before we prove it, you need to know, couple of things. One is this Chebyshev's inequality. Okay, again, the proof of Chebyshev's inequality is also very simple. It follows straight from Markov's inequality, and Markov's inequality is also not very difficult to prove. It's just a one-line proof. Do you want to see the proof, or can we just straight away apply it? I mean, if you want to see the proof, you can also watch the lectures by Blitzstein, which I've already shared with you. There's just one-line proofs, for both Markov inequality and Chebyshev's inequality. If you want me to do it, I'll do it. Just let me know. Okay. Proof of Chebyshev's inequality actually follows directly from Markov's inequality. But how to actually understand this? This says that probability that random variable x takes value uh, this much far away from mu. Okay, so at least this much far away from mu is the expectation of x. Okay, is bounded above by variance of x by a squared. Okay, so that's what Chebyshev's inequality says. There is another way to write Chebyshev's inequality. Let me give you that as well. So you can, so if you just look at this, so instead of a, we can just replace a by c sigma. Okay, so we are going to get this, probability that x minus mu is greater than or equal to c sigma is less than or equal to sigma square by c square sigma square. Okay, which is going to give us this, probability that x minus mu is greater than or equal to c sigma is less than or equal to 1 by c square. Okay, so what that means is the following, that just imagine if you put c equal to 2. Okay, so c equal to 2, if you put c equal to 2, we are going to get this probability that absolute value of x minus mu is greater than or equal to 2 sigma is less than or equal to 1 by 4. Okay, so what that means is that the chances that x takes value at least two standard deviation away from its mean. Okay, this is how you can interpret this, right? That x is taking value at least two standard deviation away from its mean. Okay, the chances of that are not more than 1/4. Okay, so so this gives you an upper bound on this probability. Okay, you can also call this a tail probability, because we are looking at the event where x is taking value far away from its mean, and this much far away from its mean, at least this much far away from its mean. So you can also think of this as the tail probability. What is the bound on the probability of the tail, x taking value in its tail? Okay, so this is the bound. Of course, if you put 3 sigma over here, you'll get 1/9. Okay, so probability that x takes value at least 3 standard deviation away from its mean is definitely less than or equal to 1/9. Is that clear to everyone? Okay, do you want me to prove this, or is that okay? Do you want me to prove Markovs and Chebyshevs, or is that fine?
But since we've run through these in stats for before, I think it's fine.
Sorry?
I was saying since we've seen the proofs before in stats for economics, we should be fine.
Oh, okay, so we can skip that. Okay, great, great, great. Okay, so this is what these inequalities are, and then convergence in probability, okay, is basically it just says the following, that if you have a sequence of random variables, okay, y1, y2, and so on and so forth, and a is a real number, okay, we say that y1, y2, yn converges in probability to this number a if so this is something that you can say that that yn takes value epsilon far away from a. That's how you can interpret this, that yn takes value at least epsilon far away from a. The probability of that goes to 0. Okay, and this should be true for every epsilon positive, no matter how small it is. Okay, so then we say that yn converges in probability to a. Make sense? Okay, so just think about it. Consider a tiny epsilon. Okay, now if so this, what does this says? This says that the chances that yn will take value epsilon far away from a, at least epsilon far away from a, no matter how small that epsilon is, the chances of that goes to 0. Okay, so what that means is yn is essentially becoming a constant. As n increases, yn is actually converging to a. Is that fine?
That's fine.
Okay, okay, so that's convergence in probability. Okay, and so now you consider a sequence of IID random variables x1 to xn. Okay, so if we generate another sequence from these IID random variables, which is a sequence of sample means. So suppose x1, x2, xn are IID. Okay, and we consider m1 as x1, m2 as x1 plus x2 by 2, okay, m3 as, again it's a sample mean, x1 plus x2 plus x3 by 3, okay, and so on and so forth, and mn is x1 plus x2 plus xn by n. So this is a sequence that you created from your IID sample. Okay, so this is known as sample mean. Okay, and obviously because these are all random variables, so sample means are also random variables. Okay, this is a random variable, this is also a random variable. So sample mean where sample size is 2 is also a random variable. Sample mean where sample size is 3 is also random variable, because it's actually an average of the random variables. So if it's an average of the random variables, so it is also a random variable. Do you agree? Okay, okay, is that fine?
Yes, Professor.
Okay, so now this is a very powerful result, law of large numbers. Okay, so it turns out that sample mean. So suppose these are ID with expectation of xi equal to mu, and variance of xi is equal to sigma square. Okay, so suppose these are ID with expectation of xi equal to mu and variance of xi equal to sigma square. If we look at the sequence of sample means, okay, so when we are talking about sequence of sample means, we are basically saying that what happens to sample means, as n goes to infinity. Okay, so the first thing that we would like to know is, of course, sample mean is a random variable. So what is the expectation of mn? So can you tell me what is the expectation of mn? What is the expectation of sample mean of size n, where
Mu.
sample is of size n? Mu, absolutely. And what is the variance of mn?
Mu squared by n.
Sigma squared by n, absolutely.
Oh yes,
Okay,
yes.
okay, is that fine? Okay, so this is the expectation and this is the variance. Okay, now we would like to know, uh, is this sample mean converging to some constant or not? Okay, and it turns out that the answer is yes, it indeed converges to a constant, and in fact it converges to the population mean, which is mu. Okay, so mn converges in probability to mu. Okay, one way to see that is that the variance goes to 0 as n goes to infinity. So basically, this random variable is actually losing its variance, as the sample size grows. So what that says is the following, that it is essentially becoming a constant mu, right? Yes. Okay, so it will be more or less concentrated around mu, for very very large sample size. Okay, and as you keep on increasing the sample size, it is just going to be basically very close to mu. Okay, and as n tends to infinity, it will become mu. Okay, so I mean, that's how you can think about it. Okay, is that clear?
Yes.
Okay, so the proof is actually just straightforward. It's just going to follow straight from Chebyshev's inequality. So probability that mn minus mu, okay, is greater than epsilon. Okay, by Chebyshev's inequality is less than or equal to variance of mn by epsilon square, right? And what is variance of mn? It is sigma square by n epsilon square, right? Yes or no? And it is obviously, since it's a probability, it is greater than or equal to 0. Okay, now limit as n tends to infinity, you can see that this goes to 0. Do you agree?
Yes.
Okay, so by squeeze theorem, this term, which is inside, which is between 0 and sigma square by n epsilon square, will also go to 0, right? Okay, and that's it. So probability that mn minus mu is greater than epsilon, mn, its limit is 0. Is this fine? Okay, so that's the proof. Have you understood this? So this shows that mn converges in probability to mu. Okay, good. Okay, now what are the applications? I mean, in fact, so there are actually lots and lots of applications. One of the applications is actually, this Monte Carlo integration. Okay, so what is Monte Carlo integration? Okay. Okay, so let's just imagine that you want to integrate some function over an interval. So you want to find the value of the definite integral, okay, of a function, over an interval. Okay, so maybe just for the example's sake, we can imagine that we are interested in integrating x square from 0 to 1. Can you tell me what is this value?
1/3.
1/3. That's right. Okay, now obviously here we know the answer, but sometimes the function that is involved is not very you know kind of, it's not very simple to actually figure out the value of the integral. So Monte Carlo integration actually offers a technique uh, through which you can actually estimate the value of the integral. Okay, and the reason why it works is because of law of large numbers. Okay, so we'll see that how. Okay, so let me first try and tell you how we can actually figure out the integral of x squared from 0 to 1 using Monte Carlo integration. Okay, and that is basically the idea behind doing integral for any other function, whichever function you like. Okay, so let's just do this. Okay, so what I'm going to do is the following. I'm going to make a square. Okay, 1 by 1 square. Okay, the reason is because I want to integrate x squared from 0 to 1. Okay, so what I'll do is the domain will be like 0 to 1. Okay, and the codomain is also 0 to 1. I mean, of course it can be bigger, but we don't really need bigger because the range of values that x squared takes when x is between 0 and 1 is 0 to 1. Okay, so that's the range of values of x squared in this interval 0 to 1. Okay, now I want to do what? I want to integrate this function, which looks like this. Do you agree?
Right.
Okay, now let's just imagine this scenario. Suppose I just think of this particular experiment, where I'll be drawing a point randomly from this square. Okay, I'll draw a point randomly from this square. Okay, so can you tell me what is the probability of drawing a point randomly from this square? Sorry, what is the probability that if you draw a point randomly from this square, it lies below this graph, below the graph of x squared?
1/3.
1/3. Is that okay? Fine. So basically, if you see, if the experiment consists of drawing a point randomly from the square, okay, so you can say that x1 y1, that's the point that you draw. Okay, a probability that x1 y1 lies below it is actually equal to the integral of x squared, right? Because that's the area, right?
Right.
Okay, so the chances that this point will lie below this graph of x squared is exactly equal to the probability, okay, that is exactly equal to the integral of this particular function, x squared from 0 to 1. Okay, now so if you really think about it, we are basically interested in finding this probability somehow. Okay, I mean, of course we know in this case that the probability is 1/3, but just imagine that we don't know this number. So basically we are interested in finding this probability. Do you agree?
Great.
Okay, so what I can do is the following. I can define an indicator random variable I1 as follows. Okay, so I1 takes value 1 if the first point that you draw from this box lies below this red curve. Okay, so how will you write that condition? You will write that condition in this way, that y1 must be less than or equal to x1 square, right? And 0 otherwise. Okay, so if that point lies below this curve, then I1 takes value 1. If this point lies above this curve, then this indicator random variable takes value 0. Is that fine?
Yes.
Okay, now can you tell me what is expected value of I1?
1/3.
1/3. That's right. Okay, basically it is the integral of x squared dx, right? Yes. Okay,
Right.
so now you can just think about it. So you are interested in the expected value of I1, right? Okay, you are somehow interested in finding this expected value of I1. So expected value of I1 can be thought of as a population mean. Okay, and I1 is just one sample. Okay, so if you actually draw a large sample, okay, so basically large number of points. Okay, if you draw a large enough sample, do you agree the sample mean will be close to this integral by law of large numbers?
Yes.
Okay, and that's basically the idea. Okay, so what we are going to do is we'll draw I1, I2, I3, In, okay, and figure out this sample mean. Let me put J over here. Okay, okay, this term, okay, will be close to this integral. Okay, this will be approximately for n large enough. Okay, and this is because of the law of large numbers. Okay, is that clear?
It's clear.
Okay, so let's quickly do this in Python and check. Okay, so let's find the approximate value of the definite integral. Using Monte Carlo integration. Okay, so let's quickly do this. So what I'm going to do is the following. Notice that what we have to do is we have to draw random numbers from this box 0, 1 cross 0, 1. Okay, so what I can do is I can draw x values from uniform 0 1 distribution, corresponding y values also from uniform 0 1 distribution, so that the pair xy is actually from this box 0 1 cross 0 1. Okay, so let's again take a large enough sample. Okay, let me first show you this using a small sample just for the picture sake. Okay, and then we'll do the integral. Okay, so let's draw maybe 100 points. Okay, yeah, so from uniform, it's uniform, right? So uniform. Okay, so x is uniform dot rvs n. Okay, that's it. Okay, and y is also uniform dot rvs n. Okay, now uh, let's just see these points, in a scatter plot. Okay, so plt dot scatter xy, plt dot show. Okay. Uh, is it plt dot point? I think. Just a minute, I have to check. Okay, so what is there in x?
The x and y axis scale is too large. Have to change the limits.
Okay, so x has this number. How is x? Okay, just a minute. Okay, where is the uniform? Yeah. Okay, RBS. Okay, I think maybe I have to specify that it's the size that I'm changing. I think that's the reason why it is. I think it is by mistake treating n as, well. It's not by mistake, but because I didn't specify what is n. So probably by default it is taking n as the location. Okay, the LOC parameter. So you have to specify that it's a size that I'm interested in. So if I take it as a size, then I think then there'll be no problem. Okay, size equal to n. Okay, now if I print x, I'll get 100 points. Okay, great. Now let's just do the plt dot scatter. Okay, earlier we just got 1 point. The reason was because it was just treating it as the location parameter and not the size parameter. Okay, plt dot show. Okay, so let's run this. So these are the points. Okay, can you see this?
Yes.
Okay, so basically, the idea here is this. Okay, let me also superimpose the graph of x square on it. Okay, p dot arrange 0 to 1, 0.01. Okay, plt dot plot. Okay, a comma a square. Okay, let's run this. Okay, so this is a graph of x squared. Okay, so the idea here is this, that you generated these 100 points, figure out the proportion of points that lies below this graph. Okay, so the proportion of points that lies below this graph will be roughly uh, approximately the probability with which point lies below this graph. Okay, that's by law of large numbers. Okay, so if you get the probability with which point lies below this graph, approximate value of that, that will also give you the integral. Okay, the approximate value of the integral. Okay, so because in this case the probability is same as the integral of x squared from 0 to 1. Is that clear?
Yes, Professor.
Okay, so let's quickly check this. Okay, let's see, with 100 data points, what am I going to get? Okay, so what I can do is y less than or equal to x squared. Okay, this is going to create the vector of booleans, the trues and falses. So whenever y is less than or equal to x squared, it's going to take value true. Whenever y is greater than x squared, it takes value false. So all that I have to do is just figure out its mean. Okay, np dot mean y less than or equal to x squared, and that's going to give me the sample mean. Okay, so let's run this. Okay, you can see that it's not bad, right? I mean, 1/3 is quite close to 32%. Okay, now of course, if you just increase the sample size from 100 to 10 to the power 5 or something like that, the approximation will be much better. Okay, let's quickly do that as well. Okay, okay, let's run this. Okay, as we can see that we have actually improved our approximation because we have taken a larger sample size. Is this clear?
It's clear.
Is this fine? Okay, so this is how you can actually use law of large numbers to integrate a function. So obviously here we knew the integral, so we could easily verify. But for functions for which integral is not very convenient to find, you can still use law of large numbers to estimate the integral. Of course, in that case, you'll not be able to verify or check, but there is no need for it. The reason is because of law of large numbers, we know that the value will be close to the actual value of the integral. Okay, is that fine?
Yes.
Okay, okay, so okay, so this was Monte Carlo integration. Obviously, this is not just true for functions which are defined from 0 1 to 0 1. It is also true for any function defined from let's say AB to 0C. So of course, if the function take negative values, then you may have to deal with it in a different way, but still you can use Monte Carlo integration, okay, to do that. But let's say if it only takes non-negative values, then it is straightforward. Okay, just just look, so suppose the function is defined on AB, okay, closed interval AB, and it takes between random variables, which takes value ij equal to 1 if yj is less than or equal to fxj and 0 otherwise. Okay, and then these are all Bernoulli random variables with probability that is precisely equal to the ratio of the area below f to the area of the rectangle AB cross 0c, right? Okay, so expected value of ij is just uh, the area below the graph divided uh, by the total area of the rectangle. Okay, is that fine? Yes or no?
Yes,
Yes.
Professor.
Okay, and if you are interested in approximating this integral, then all that you have to do is because this p is the expected value of ij, so by law of large numbers the sample mean, so summation ij by n, okay, summation ij by n will be approximately equal to expectation of ij. Okay, so summation ij by n is approximately equal to expectation of ij, and expectation of ij is exactly equal to this. So all that you have to do is you will get that the integral of fx dx by c upon b minus a is approximately equal to summation ij by n. And if you take c into b minus a to the right hand side, so just take the sample mean multiplied by c into b minus a, which is the area of the rectangle, and that's going to give you the approximate value of the integral of fx from a to b. Is that clear?
It's clear.
Okay, so let me give you a question. Okay, why don't you do that? So I'll give you 5 minutes to approximate the integral. Okay, fine. Okay, so suppose you want to integrate from 3 to 5. Okay, let's say x squared minus sine x dx. Okay, so suppose you want to do this. Okay, uh, so you can try this. Okay, notice that it's non-negative. Okay, defined on a closed interval. Okay, so it's everything is met. Okay, everything, all the conditions that we have written are true about this particular function. So you can now do the integral. Okay. Okay. So I think np dot sign should be something. Okay, let's see, np dot sign, np dot pi. So you can actually use np dot sign. Okay, Okay, okay. So let's quickly do this. So okay. So first of all, let's figure out the rectangle. Okay. So what we can do is so x square is 25, right? I mean, when x is 5, it's 25, and when x is 3, it is 9. So what I can do is so of course, you can just start with 0. That's not a problem. You can just start. So the 0 to 0 to 26, that's actually kind of uh, fine, right? Because x square minus sine x can never be above 26. Okay, so 0 to 26 we can take as we can consider 0 to 26 as the height of the rectangle. Okay, and 3 to 5 as the length. Okay, and then we can just apply Monte Carlo integration. Okay, so let's do this. Okay, okay. So x equals uh, uniform dot rvs. Okay, okay. So the location in this case will be so x values are from 3 to 5, right? So location parameter will be 3. Okay, scale parameter will be 2. Okay, because you want from 3 to 5. Okay, and size, the sample size will be n. Okay, okay. So this is x. Okay, let me just take 5 values and print it out just to see if this is giving me. Yeah, so it is giving me values between 3 and 5. Okay, so now I can just take n over here. Okay, now the corresponding y values are from 0 to 26. So this is 0, this is 26. Okay, and now I just have to check what percentage of them have this property that they are below x square minus sine x. Okay, so that they below, so I can just print out np dot mean, and y is less than or equal to x squared minus np dot sine x. Okay, is that fine? Okay, and let's run this. So it's just going to be approximately 65332. Okay, if you want to quickly check your answer, if you want to do that, you can do it. Oh, sorry, this is, oh, just a minute. You have to also multiply this by multiply this whole thing by the area of the rectangle, right? I mean, this is just a proportion. Okay, so you have to also multiply this by 26 times 2. Okay, so 52 star. Okay, now this is fine. Okay, so it should be around approximately 33 point something. Okay, so you can actually apply this to any function, I mean, for which you don't know the integral. I mean, and then whatever value you get over here can be used to approximate as an approximate value of the integral. Okay, so that's one application of law of large numbers. Of course, there are many of them. Okay, so another application is figuring out the empirical CDF. Okay, so what is the empirical CDF? We have already seen empirical CDF earlier. So it's just basically the empirical distribution, which is something that you get by drawing a large sample from the population. Okay, so if you draw a large sample from the population, look at the distribution of this. Look at the distribution of the sample. Okay, I mean, so basically, just look at their histogram. That's what I'm saying. So you draw, let's say, 10 to the power 5 observations or 10 to the power 6 observations, and look at the histogram plot. Okay, and that's going to give you the empirical distribution. And it turns out that the empirical distribution will be quite close to the actual distribution from which this sample is drawn because of law of large numbers. Okay, and this is something that I've already told you, but here we can actually prove it. Okay, that it will be quite close. So again, suppose x1 to xn are ID random variables with CDFF. Okay, so CDFF, F is your population distribution. Okay, and these are all ID random variables. So basically, this is a sample which is drawn from this distribution or CDFF. Okay, now what you can do is you can define Rnx. Okay, so Rnx is basically the total number of xi's which are less than or equal to x. Okay, so it's basically total number or total count of xi's which are less than or equal to x. Okay, and what we can do is the following. We can divide this whole thing by n, which is going to give you the proportion of xi's which are less than or equal to x. Is that okay? Yes or no?
Yes, Professor.
Okay, now if you look at this indicator xi less than or equal to x, can you tell me what is the expected value of this indicator xi less than or equal to x? What is the expected value of I xj less than or equal to x? So it's an indicator that indicates whether xj is less than or equal to x or not by taking value 1 or 0. So if it takes value 1, then xj is less than or equal to x. If it takes value 0, otherwise, if xj is greater than x. So can you tell me what is the expected value of this?
So it's the value of the CDF.
It's a value of the CDF at x. Is that fine? Okay, so which is nothing, which is basically f of x, right? So what we have here is this, if you look at this whole thing divided by n, it's actually, the sample mean. Okay, where each of these random variables have expectation fx. So if each of these random variables have expectation of x, and if you divide this whole thing by n, that's the sample mean, then by law of large numbers, the sample mean, which is the proportion of points that lies below x in the sample, actually converges to the population mean, which is actually the CDF, the value of the CDF at x. So if you look at this proportion, this proportion is actually the empirical distribution. Okay, and this empirical distribution will be close to the actual distribution because of law of large numbers. This is the proof. Have you understood this?
Yes, Professor.
Okay, yeah. Okay, so that's exactly what we have over here. The empirical CDF is f hat n x, which is the proportion of points, and this is actually the sample mean, of these indicator random variables whose expectation is fx. And because it's a sample mean, as n tends to infinity, this goes to the actual fx, in probability. Okay, so by law of large numbers, f hat n converges to fx in probability, and therefore can serve as a reasonable estimate of fx when n is large. Okay, is this clear? Okay, now let's do few more applications of this. Okay, and then we'll move on to another very interesting result, which is central limit theorem. Okay. Okay, so let's see. Where is it? Yeah. So what I'm going to do is this, that I'll give you a problem, where you have to actually use law of large numbers to figure out the solution to a problem. Okay. So okay, so let's estimate these quantities. Okay. Probability that x takes value less than or equal to 1, okay, when x is normal 0 1. Okay. Okay. Find the probability that estimate the probability that x is less than or equal to 1 when x is exponential 1. Okay, of course we can also find the actual probabilities in this case, because we know how to do that, but I'm just doing it because so that that we can also use law of large numbers to estimate these quantities. Okay. So this is something that we are actually trying to figure out the empirical CDF at 1 of x, and here also we are trying to figure out the empirical CDF of x at 1, when x is exponential 1. Okay. So let's do this exercise first, okay, and then we'll do more. Okay. So okay, let's maybe do another one. Estimate the value of expectation of x, okay, when x is uniform. 3 to 5. Okay, fine. So let's do this exercise quickly. Okay, and then we'll do some problems where finding the actual values is not very easy. Okay. And then we can actually uh, uh, use law of large numbers to estimate it. Okay. So let's quickly do this. So let's do the first one. So let me do the first one, and then you do the second one and the third one, and you tell me what you have done. Okay. So again, I'll take a large sample. Okay. Let's say 10 to the power 5. Okay. And I want to estimate the probability that x is less than or equal to 1. Okay. So what I'll do is, I'll take norm dot rvs. Okay. So I'll generate, a sample of size 10 to the power 5 from standard normal distribution. Okay. And then I'll figure out the proportion of points that lies below 1, right? I mean, that's what we do, right? I mean, in empirical CDF, you figure out the proportion of points in this sample that lies below 1. Okay. So what is the proportion of points? So how will you get that? Let's call this x. Okay. And you just take np dot mean. Okay. X less than or equal to 1. Okay, and that's going to give you the proportion of points that lies below 1. Okay, we can print this out. Okay, So this is by law of large numbers, you know, should be approximately equal to the probability that standard normal random variable takes value less than or equal to 1. Okay, we can quickly check this. Okay, so print norm.cdf. Okay, so we have to evaluate the CDF at 1. Okay, so let's just check, and you can see that it's just quite close, right? I mean, this is your empirical, using the empirical distribution you found the proportion, and this is the actual probability, and it turns out that they're actually pretty close. Okay, uh, you can do the same thing for the second one. Okay, so n is 10 to the power 5, so of course I don't have to define it again. X is x own dot rvs size equal to n. Okay, and then print np dot mean. Okay, x less than or equal to 1. Okay, okay, and we can also at the same time print the actual value, okay, of the CDF. So expon dot CDF evaluated at 1. Okay, let's quickly check. You can see that again, it's just pretty close. This is the empirical approximation. Okay, 63171, and this is the actual probability, which is also not that far away from the empirical approximation. Okay, let's do the next one. Expected value of x. So we know the actual value of the expected value of x, right? I mean, what is the actual value of the expected value of x when x is uniform 3 to 5?
4.
4, right? So we know that. Okay, let's quickly see if we draw random numbers from 3 to 5. What are we going to get? Okay, so again I'm going to draw uniform RVS. Okay, size equal to n. Okay, location is 3. Okay, scale is 2. Okay, and this time I'm going to take np dot mean x. Okay, because now I'm not interested in the proportion. Okay, now I'm interested in the actual x values, right? So what I'll do is I'll take the sample mean of these x values. So sample mean of these x values will give me approximately equal to the population mean, which is 4. I mean, which should give me approximately equal to the population mean. And let's run this. Okay, and that's not pretty bad, right? That's pretty good, right? I mean, it's just very close to 4, right? So this is basically the power of law of large numbers. You can actually, if you don't know the population mean, it's obviously more useful when you don't know the population mean, and it's very difficult to know. Like in reality, when you're drawing sample from a huge population, let's say you are interested in figuring out the average income of the country. Okay, and let's say you don't have the data on like all the people of the country, income data of the entire population. You don't have the income data of the entire population. So what you can do is you can just draw a sample of a large sample, maybe a sample of 10,000 randomly, from the entire population. Ask them to report their income, assuming the reports are correct. Just figure out the average income, from those reports, and that is the sample mean. And because you had drawn a random sample, from that large population, that average income of that sample will be quite close to the population average. I mean, I'm not saying it will be exactly the same, but there is a possibility of also making huge errors, but that's very unlikely. Okay, so with large samples, that's a very good thing, that it is very unlikely to make errors which are big. So you can actually trust the sample mean you know, as an approximation for the number that you're interested in, which is the average income of the entire country. Okay, and that is not just true for any, you know, like it is true for any kind of problem, you know, where you are interested in some unknown quantity, and then you draw a large sample, and you know, you just figure out the average, and that average will work as a good uh, approximation for the true mean that you are interested in. Okay, it can be a proportion, it can be the average mean of the income, or it can be the proportion of people earning below a certain level of income, you know, something like that. Is this fine? Like you can also think about, you know, let's say that there is some poverty line, you know, you want to figure out what percentage of the country is living below the poverty line, you know. So how do you get that? Again, you know, either you figure out the income of all the individuals, and then, you know, figure out you know, what percentage of people are earning below the poverty line, you know. Another way is basically, you know, you can just draw a random sample, you know, which is large enough, and figure out in that particular sample what proportion of people are below the poverty line. And as we have seen that this is the empirical CDF, okay, and this empirical CDF will be quite close to the actual CDF. So so percentage of people in that particular sample who are below the poverty line will be a good approximation of percentage of people who are below the poverty line in the entire country. Make sense?
Yes, Professor.
Okay. Okay. So let's do one more problem. Okay. So this time what we have to do is, so we don't know the exact distribution, but you know, we'll still figure out an approximate probability. Okay. So suppose x1, x2, x3, and x4 are IID uniform 0, 1. Okay, so you have to figure out you know, an estimate for the following. So estimate the following: the probability that x1 plus x2 plus x3 plus x4 is less than or equal to, let's say, 1. Is the question clear? Now, okay, now figuring out the exact distribution of x1 plus x2 plus x3 plus x4 may not be very easy task. You know, of course, you can do it in 2 steps. You can use convolution to figure that out, but it's just going to be time consuming. Okay, but you can actually still estimate the empirical CDF of x1 plus x2 plus x3 plus x4 using the technique that we have just seen, and you know, and that's going to be pretty close to the actual value. So why don't you do this? Okay, is the question clear?
Yes, Professor.
Okay, so why don't you do this? Write a code, do this problem, and you know, send me the code. You have 5 minutes, and then we'll see. Okay, so you just have to figure out the value of the empirical CDF of x1 plus x2 plus x3 plus x4 at 1. Okay, okay, so let's quickly do this. So again, you know, you can just choose a large sample size, okay, so that your estimate is close to the actual value. Okay, so you can just generate, because uniform 0 1, so you can generate 10 to the power 5 values from uniform random variable. Okay, so location is in this case 0, scale is 1, so which is by default, so we don't have to specify that. Okay, and then you do the same thing for x2, do the same thing for x3, and do the same thing for x4. Okay, so now you have basically generated 10 to the power 5 values of x1, 10 to the power 5 values of x2, and 10 to the power 5 values of x3 and x4 and so forth. And now if you want to see how the distribution looks of x1 plus x2 plus x3 plus x4, you can you can just define a y as x1 plus x2 plus x3 plus x4, and then just simply do the plt dot hist y and plt dot show. Okay, that's going to give you some idea. This is like kind of empirical distribution. Let me just increase the bins. Okay, let's say bins is 30. Okay, so this is how it looks. Okay, now this is the empirical distribution, and it is quite close to the actual distribution. So all that you have to do is just have to figure out the proportion of points that lies below 1. So just figure out the proportion of points that are below 1. That's all that you have to do. Okay, so that is actually straightforward. Uh, now you already have y's. Okay, so np dot mean y less than or equal to 1. Okay, and that's it. That's just going to give you the approximate probability. Okay, which is basically 4.2%. Okay, so basically there's a 0.042 probability or chance that the sum will be less than or equal to 1. Is this clear?
Yes, Professor.
Okay, now so now let's move on to the next result, which is again very interesting, very powerful. Okay, so this result says that if you look at the sample mean, okay, so if I look at the sample mean, which is so let me use mn. Okay, so sample mean converges in probability to mu. We know this by law of large numbers. Okay, so what that means is that its variance actually goes to, we know that its variance goes to 0 as n tends to infinity. Now what can you say about mn minus mu? So obviously if mn converges in probability to mu, mn minus mu will also converge in probability to 0. Do you agree? Okay, now if I divide this by the standard deviation of mn, which is sigma by root n, what can you say about this object? Notice that the variance of this is always 1. Okay, so variance of mn minus mu is sigma square by n. Now what I've done is I've just converted this mn minus mu to mn minus mu upon sigma by root n. Notice that variance of this is always 1. Now obviously if you look at this particular random variable, this random variable doesn't converge in probability to a number. Do you agree? Because because we are able to preserve the variance. Okay, and it turns out that this particular random variable converges in distribution to standard normal. Okay, so if you are preserving the variance, variance is 1 throughout, then we would like to know what is the limiting distribution of such a thing, okay, or such a random variable. So it turns out that the limiting distribution of mn minus mu upon sigma by root n is standard normal, okay, which is central limit theorem. Is this fine?
Yes, Professor.
Is that okay? Okay, now how can we use it in applications? Okay, so for applications purpose, this is CLT. Okay, for applications purpose, we obviously we never have an infinite sample size, so we just consider n large enough. Okay, for n large enough, mn minus mu upon sigma by root n, we'll say that it is approximately standard normal. Okay, and what that means is mn minus mu is approximately normal with mean 0, variance sigma square by n. Okay, and what that means is mn is approximately normal with mean mu, variance sigma square by n. Sorry. Is this fine? Is that okay?
Yes.
Okay, and if you look at summation xi, notice that this is nothing but n times mn, right? I mean, you just multiplied mn, which is the sum of xi's by n, so that will be approximately normal with mean and mu and variance and sigma square. So these are ways in which you can actually apply it. Instead of using the actual distribution, you are using normal distribution as an approximate distribution of the sample mean or the sample sum, when n is large enough. Okay, and how much is large enough? Well, it usually depends on the population. So if the population is kind of symmetric, even n equal to 20 is kind of large enough. Okay, but if the population is not symmetric, then it totally depends on how long will the sum take to actually become symmetric. Okay, so there is as such no thumb rule. I mean, you can say sometimes you treat 30, 40 and 50 are kind of as large enough, but of course, you can always have distributions which are very asymmetric to begin with, and then even with n equal to 50 you may not be able to get uh, kind of a good normal approximation. So it usually depends on the kind of population from which you are picking it. Okay, but as I've told you, like for most scenarios, most distributions, 40 50 is considered to be a large enough sample. Okay, which is good enough to actually use normal distribution as an approximation. Is that fine?
That's fine.
Okay, so let's do a problem. Okay, so what we are going to do is the following. So suppose x1, x2, x100 are IID uniform 0 1. Is that okay? Fine. Now what you have to do is you have to tell me what is the probability that x1 plus x2 plus x100 is between 45 and 55. Okay, so basically two ways to do it. Because this is the sum of id random variables, so the approximate distribution will be normal. So one way is by using CLT. So by CLT, so figure this out by CLT. Also figure this out by law of large numbers. Okay, so you can also figure out this by law of large numbers. Okay, I mean, we can apply both the methods, right? Okay, because now the sample size is actually 100. So if it's 100 sample size, 100 is large enough. So we can actually use normal approximation, for the distribution of x1 plus x2 plus x100. So if we can use the normal approximation, we can actually use the central limit theorem to figure out this probability. So that's one way to do it. Another way is which we have just done, earlier. So we can also use law of large numbers to do it. Okay, so let's do this problem quickly and then we'll stop. Okay, so let's do this. Okay, so let's first do this using CLT. Okay, so using CLT, okay, we know that it's a sum, so obviously it is approximately normal. Okay, but we have to figure out the parameters. So can you tell me what are the parameters? What is the expectation of this? What is the expectation of this sum if these are uniform 0.01. What is the expectation of this sum?
Half.
Huh? 50, right?
So, it should half.
Yeah, 100, half plus half plus half, 100 times is going to be 50. And variance of each of them is 1 by 12. Okay, and since these are independent, so some of the independent 100 independent random variables, each of them has variance 1 by 12. So you're going to get 100 by 12 as the variance of this sum. Do you agree? Okay, now this is straightforward, right? I mean, the distribution which is of this x1 plus x2 plus x100 is approximately normal 50, 100 by 12. So if you want to figure out that it takes value between 45 and 55, then all that you have to do is just have to use norm.cdf. Okay, location is 50. Okay, scale is square root of 100 by 12, which is 10 by square root of 12. Okay, so that's a scale. Okay, and you have to figure it out, between 55 and 45. So 55. Okay, minus 45. Okay, and you can print this out. Okay, so that's basically close to 91%. Okay, is that fine? Is that okay? Okay,
Yes,
now
Professor.
let's quickly do this for using law of large numbers. Okay, so of course you don't want to create x1, x2, x100. Okay, I mean, it's just a lot of steps. So you can actually create a single matrix. Okay, and then use row sum or column sum or something like that. So let me do that for n equal to 10 to the power 4 first. Okay, so it will give you 100 by 100. Okay, so what I'm going to do is this, that I'm going to generate uniform. Okay, uniform numbers. Okay, so x is, okay, and then I'll just do the reshape thing. Okay, x dot reshape. Okay, and then you just have to specify 100 into n by 100. Okay, okay, and then you take np dot sum. Okay, x, was it 1 or 0? Okay, let's just try this. Okay, let's just print out this. Okay, sorry. Yeah. Yeah, now this is fine. Okay. Okay, so this is I'm interested in basically this. Sorry about that. Yeah, this is fine. Okay, so basically if I do np.sum x0, it is going to give me 1000 values of x1 plus x2 plus x100. Okay, so let's call this y. Okay, and let me do this 10 to the power 6 so that I get 10,000 values, which is a large enough sample, and then I can use this to figure out the proportion of values that lies between 45 and 55. So np dot mean. Okay, so I have to figure out the proportion of values that lies between 45 and 55. So y is less than or equal to 45. Sorry, greater than or equal to 45. Okay, so okay, and then just divide this whole thing by 10 to the power 4. Okay, and you should get this. Okay, so let's print that out. Oh, what is this? Oh, sorry, this should be 45. Yeah, okay, so you can see that this is also close to 91%. Okay, so this is by law of large numbers, and this is by central limit theorem. Okay, and we got approximately the same answer. Okay, so again, none of them is accurate, because the actual distribution of x1 plus x2 plus x100 is something that we don't know. Okay, but they are going to be approximately equal to the actual probability by, this is by central limit theorem and this is by law of large numbers. Is that clear to everyone? Okay, so this is how you can actually solve problems through simulations. Okay, this is also, like, simulation is also the word that is used for it. So you can actually determine these unknown quantities by simulations in this way. Okay,